Hello and welcome to our day 2 notes for Upward Bound Advanced Math. Today we're talking about complex numbers, okay, and specifically we're looking at uh, the operations of complex numbers and some of the more basic ones, but just so we get an idea of where complex numbers come from, where they happen, that kind of idea. So I just wanted to start off with a question, and my question is, what seems to be the main goal of any high school math class? Deep down inside, I think the main goal of any class, you could argue with the exception of geometry, but that's even involved in there quite a bit, is solving equations. That's what I would say. That would be my I guess, opinion, is solving equations. So in solving equations, we come across ones like this quite a bit where, we want to get x by itself. So x equals 4, take the square root of both sides, and we get x equals, you could say 2 or plus or minus 2, whichever way you really saw that. Most of the time in this class, I'm going to deal with what we call the principal square root, and just saying that this is x equals 2. Well, what if I try to solve this one? And I guess the main question is, what is the difference between these two? Well, pretty simple difference in that this one says x squared minus 4. This one says x squared plus 4. But when I go to solving this equation, I get x squared equals negative 4, and then I try to take the square root of that. Now, if I do that on a calculator, at least I'm not going to say a lower level calculator, but really anything but the highest functionality calculator is going to give me an error. It's going to probably say domain error, in that if I'm looking at the square root of negative numbers, that's not actually in the domain of the square root function, so it's not going to work. And so that kind of brings light to a new number, so to speak. And that number is the square root of negative 1. The reason we use square root of negative 1 as the number I, or I guess where that comes in handy, is that this can be written as the square root of negative 1 times 4, which with the square root world means that I can separate this out into the square root of negative 1 times the square root of 4. Square root of 4, again, thinking of what we call the principal square root as just the positive one. I could talk about positives and negatives. That's not a bad thing to do, but it's also not always 100% necessary. And then I have this square root of negative 1 idea. Well, that's just I. We're going to call that I in any math class, I guess. And really, there's two ways that I is defined. You're either going to see this one where I is the square root of negative 1, or you'll see it written this way, that I squared equals negative 1. Meaning that I times I would give me negative 1, but that's saying the same thing. If I take the square root of both sides, I'm going to get I is equal to the square root of negative 1. So either way that we see that, those are two ways that it's defined. So bringing that to light in our normal number system, our real number system, we don't see that anywhere. We don't see any ideas of I's or what we call complex numbers. And I do apologize that this is hard to read. I'm hoping that it's better on your paper versions, but it still might not be. And I apologize for that. But let's see what we've got here. So if you're not familiar with the real number system, we've got naturals, wholes, integers, rationals, and real numbers. Sorry. And real numbers are actually split into these two categories of rational numbers and irrational numbers. Just because this is smaller doesn't mean that there's less of them. We just kind of think of them as less populated, like on a number line. They're sparser. There's more space in between. But you could actually argue that there's plenty of mathematical arguments that there's as many irrationals as there is rationals, even though we don't see it that way. Okay, but that's all from other math classes. Those are the numbers that we've always dealt with. We've always dealt with rational, irrational. We might not have always used the words, but those are all the numbers that we've worked with before. Not to say that you haven't worked with complex numbers, because again, we're dealing with people with various mathematical backgrounds, and I'm trying just to teach kind of a blank slate approach. So this other version of the number system includes complex numbers. So if you notice this little, I'm not going to say little, but littler area right here, that's this just transferred into our new picture. So realistically, the real number system is not, I'm not going to say it's not complete. It is in fact the real number system, but we have numbers that aren't real. Okay. So complex numbers are an expansion on the real number system, where I have a plus bi. That's a pretty common writing of a complex number. Within those complex numbers, technically those are called imaginary numbers, where I have some number in the form of b. So a plus bi, where b is not 0. That makes up an imaginary number. Okay, and then we have a kind of a subgroup of that is the pure imaginary numbers, where there is no a. It's just a number times I. So that number that we came up with as the example here, the solution to this equation is a pure imaginary number, because there's no a in front of this. There's no a plus 2i. It's just 2i. Okay. So what that really means, and we always kind of throw around the word real numbers, but what that really means is that all numbers that we've worked with are what we call complex numbers. If there's no, I want to make sure that I'm not taking anything away from before. No, if there's no imaginary part to the number that you have as an answer, if your answer is something like 1/2, 1/2 fits in here. It's just plus 0i. There's no imaginary part. So you can just say that it's 1/2 plus 0i. 1/2 is the a part, and 0i is the imaginary part, and there we go. It's a complex number. It's very boring when it comes to the idea of complex or imaginary numbers, but it still fits. Okay. So then for the definition of complex numbers, it's just an expression of the form a plus bi, where a and b are real numbers. And I is the square root of -1. Okay. This is where we get some kind of variance in definitions. I guess not here, but the second part of this. We say verbally that a is the real part of a complex number, and b, this is where I kind of differ. One definition I read said that b is this other part, and I've always thought of bi as being this part, but it is called the imaginary part. Okay, so b or bi, it doesn't matter either way. Now, yeah, so for adding and subtracting complex numbers, And by this, so there is a difference. I do want to say there is a difference between complex numbers and imaginary numbers. It's a very subtle difference, and it's a very technical, I should say, difference, in that you can kind of use the two phrases to mean the same thing. But complex numbers can be all of these real numbers that we've always worked with, where imaginary numbers technically can't. The key with imaginary numbers is this part that's really hard to read on my screen, maybe not so much in your book, but that the b can't be 0. For it to be an imaginary number, it has to have the imaginary part, as in there has to be something times I other than 0. Okay, now it can be a fraction, it can be a decimal, it can be any real number, but it has to be just that. It has to be real. And I guess not non-zero real, to be precise. So operations-wise, it's not overly difficult. It looks sort of complicated, but in the end, it's not really that bad. For adding and subtracting, we just combine the real parts and the imaginary parts. So if I look at, and my suggestion, I should start with that. My suggestion would be always focus on adding. If it says subtraction, if there is subtraction, like in this first problem, I'm just going to change it to an addition problem. Now, obviously, I can't just say plus and go at it like normal, but I can change this one by distributing that negative first. So that is my suggestion. So I've turned this into, instead of negative 4 plus 7i, 4 minus 7i. And I'm using addition. Now, the parentheses aren't exactly necessary, but that's how we view those complex numbers or those imaginary numbers. So I've just thrown them in there. In the end, they don't really matter because I'm going to combine my real parts. 2 plus 4 is 6. And my imaginary parts. Negative 5 and negative 7 is negative 12. Now, of course, you could think about like factoring out. I mean, these are both multiples of 6. You could factor out 6. That's not going to do us much good. We want to know the actual value of this. So we like to see it as 6 minus 12i. For addition, again, it's pretty simple. I'm just going to combine my real parts. Oh, but here I have 4 and I have minus 4, so that's like 0. And my imaginary parts, I have negative 5i and positive 6i. So that's going to be plus 1 or just plus I. Sorry, plus 1i or just plus I. And with that 0 there, you don't have to write it. You can just say that it's I. So technically, if we're looking at our breakdown of these numbers, since the a is equal to 0, this answer is a pure imaginary number. And that's kind of cool. Last one we have here, I have 5 and negative 5, so that's going to be 0, and then negative 7i plus 7i, that's 0i. And the easiest way to write this is just to go with 0. Okay, everything kind of canceled out, so to speak. And for the second page, we're going to start talking about multiplying complex numbers. And again, this will feel fairly familiar. Okay? It says to multiply them like binomials. Well, what would I do with binomials here? Well, I would FOIL, or whatever phrase you've used to mean that same process. So I'm going to go first times first. Negative 2 times negative 2 is 4. Negative 2 times positive 2i. That's going to be a minus 4i. I times negative 2 is negative 2i. And I times 2i is plus 2i squared. Now we reach something very special right here. We have another phrase or another notation for I squared. The key to all of this is that whenever we get an I squared, we can replace that with a negative 1. And that's why sometimes the definition of I is written in a different way. Sometimes they will say that that the way you define I is that I squared is negative 1, because you'll see that come up quite a bit, and we just make a quick switch. Any answer with an I squared in it is technically not as simple as it can be, so it's technically wrong. So we have, why don't I go ahead and simplify a little bit. I'm going to combine my two I terms to be negative 6I. And I'm going to make that switch of I squared being negative 1. So 2 times negative 1 will be, you could say plus a negative or just minus 2. So that really, that I squared part adds to my real part of my complex number. And so I have negative 2 and 4. That's going to be 2 minus 6I. The next one, same idea. I just want to FOIL. Negative 3 times 7 is negative 21. Negative 3 times 3i is negative 9i. Negative 2i times 7 is negative 14i. And just like the last time, this last one I'm going to be multiplying two i's together. I'm going to have negative 2 times negative 3, so that's negative 6. And I'm going to have I squared. Again, I squared equals negative 1, so we multiply negative 6 by negative 1, and we end up with a positive 6 here. Okay. So you could almost think about like, that's not really that. That's actually positive 6. And kind of cut down the amount of work that you, and then the amount of, it's not less work, but it's kind of less writing. I'm going to combine that negative 6, or sorry, that positive 6 and negative 21 to give me negative 15. And my i's will combine to be a negative 13. Okay, let's look at this last one here. Negative 5 times negative 5 is positive 25. Negative 5 times negative 8 is negative 40. And that, again, positive 40. 40i. Wow, I'm battling my negatives today. 8i times negative 5 is going to be a negative 40i. And let's see, positive 8i times negative 8i is going to be negative 64i squared. Again, this negative 64i squared, I squared is negative 1. Negative 1 times negative 64 is plus 64. So those cancel out. And here I have 64 and 25, which is, let's say, 89. And then what happens with my I terms here? I have negative 40 and positive 40, so they cancel out. Or they become 0i, which just gives me 89. So hopefully what you notice out of that last answer, as we just did it, is that my i's cancel. And really what that means is I no longer have, it's not that I don't have a complex number, because again, complex numbers are everything that we've dealt with, but I don't have an imaginary number. So it's not imaginary. And why could that be? What forced that to happen? What made that idea of the 40 i's canceling out? Well, it's somewhat like a difference of squares. If you remember that from your, or sorry, not difference of squares. I apologize. Um, hold on. Sorry about that. I had to answer a phone call. So why is that? It is, I negated myself, but it is somewhat like a difference of squares in that the backwards direction, sort of the backwards direction of a difference of squares, where I sort of factored out my 25 minus 64i squared. If I were to factor that out, I would factor it into this. And so, yeah, it is that idea of difference of squares. In the math world, we don't call that a difference of squares because that's just kind of a weird way to look at it. It's actually called the conjugate. And in this case, since we're dealing with complex numbers, it's called the complex conjugate. So the definition here is the complex conjugate of a number z, which we say is, in this case, a plus bi, is formed by the real part and the opposite of the imaginary part. And what that means is that the complex conjugate of z would be a minus bi. And if we look up here, that's really what we did. If this was a plus bi, we multiplied it by the same a, but minus bi. And obviously, if our original one was minus here, we'd just make the second one a plus, and there we go. But what does that do? Again, it makes it not imaginary. It makes it a real number now. And the reason that's important is that when we come to dividing complex numbers, I use this term very kind of loosely in this case, we call it rationalize the denominator, and technically it's kind of like, not that this really means the same thing, it would help if I spelled it right, it's kind of like realizing the denominator. Instead of making it an imaginary number, we're making it a real number. Because I know that whenever I multiply, now this one is a little bit weird. The real, sorry, bad word to say, the actual imaginary number down here is 0 plus 3i. So its conjugate would be, if I'm going to multiply by the conjugate, it's going to be 0 minus 3i. I might have said minus there, but either way. But I don't need the zeros, obviously. So I'm actually going to erase that. And all I really need to do is multiply this by negative 3i. And I know that that's going to turn into a real number. But remember, when we're dealing with any numbers, we can't just do something to the bottom. That's going to change this number entirely. I don't want to change it. I just want to come up with a new way to look at it. So I have to do that same thing to the top. Okay. Now on the bottom, I have 3i times negative 3i. That's going to be, I guess I'll give myself some room here. That's going to be 3 times 3, and 3 times negative 3 is negative 9, and I have I squared. I will simplify that in a second, but let's look at what happens to the top. 5 times negative 3i is going to be negative 15i. The I squared again turns into negative 1, and negative 1 times negative 9 is positive 9. So my bottom is 9, top is 15i. And then I can just simplify like usual, dealing with my sort of reducing fractions idea. They're both multiples of 3, so this turns into 5 over 3i. Sorry, 5i over 3. I realized I said that wrong. Kind of weird in the case like that it just sort of moves the I to the top. Again, special case. For the second one, I actually have a complex number here, so I want to deal with the, sorry, I actually have an imaginary number, so I want to deal with the complex conjugate, and I want to multiply that by -3 plus 7i. And this one we'll see that we actually drastically change our answer as opposed to the first one. So in simplifying this, I'm going to have -3 times -3, that's going to be 9. -3 times 7i is -21i. -7 times -3 is positive 21i. And -7i times 7i is going to be -49i squared. On the top, it's just like a distributing problem. So I'm going to have -12 and plus 28i. To simplify all this, the reason we chose to multiply by this is to actually get rid of all this. So that stuff will all cancel out. And then remember, I squared is -1, so this is positive 49 plus 9 is 58. So my new denominator is 58. And my numerator is that 12 plus 28i. Okay? That's what I come up with as an answer. And then, not that it's really the case on this one, but remember to reduce any of this, I would have to have, well, I guess I could on this one. Let's actually do that. Let's make this a little bit more simple. I'm going to factor out I think 2 is the best I can do. Yeah. I'm going to factor out a 2 from this. So I'll have -6 plus 14i. And then down here, if I divide this by 2, if I divide my 58 by 2, I get 29. And now my 2's will cancel, and that is about the best I can do. So I have -6 plus 14i over 29. Okay? Give me a second while I clean this up a little bit. Okay. So I just wanted to, I don't like erasing anything because I know that sometimes students want to see it. So I would rather just make it a little smaller. You can obviously always rewind and go look at it that way. Last problem that we'll do, again, I want to look at this process of rationalizing or realizing the denominator by multiplying by the complex conjugate of the denominator, and that's going to give us -5 times -5 is going to be 25. I'm going to get positive 10i, negative 10i, and -4i squared. Again, that part cancels. That becomes a positive 4, so on the bottom we get 29. On the top, I'm going to have -3 times -5 is 15. -3 times -2i is going to be plus 6i. Positive 10 times 5, -5 is -50i. And positive 10 times -2i is going to be -20i squared. So in this one, because there was a complex number on the top as well, we have to still kind of combine like terms and turn this into a positive 20 and add it to the other one. So I've got 35i, sorry, just 35. And then this will be a -44i. So we had that same process of having to simplify that, but the i's didn't cancel like they did in the bottom, and they probably won't. There may be a case where they would. Okay, so I hope that helps, and we will see you in class.